All right, now that you're finished assignment 6C1, when you roll into class tomorrow, you'll see this. We've got all the normal stuff, unit circles there, sine, cosine, sketch those graphs. Now here's the new stuff. Reciprocal pairs. What's the reciprocal pair of sine? What's cosine? What's the reciprocal pair of tangent? And how is tangent defined in terms of sine and cosine? So the answer is this. Sine and cosecant, cosine and secant, tan and cotangent. These are the reciprocal pairs. Tangent is defined as sine over cosine, like that. So you can see we've got all the other normal stuff right there, and these are the things you have to have memorized. And if you have those things memorized, then the section for today, section 6.32, might be a little easier for you. You can, of course, figure out those things, but you'll have a lot more brain power left over to learn new things and to use them if you talk about today. Now, today, holy cow, look at all these numbers. If you're the kind of person who is overwhelmed very easily by large tables or data tables, then just take a deep breath right now and just trust the process a little bit. Just know that I'll try and explain as much as I can here, and you can, of course, always bring your questions to class. But I wanted to just first of all walk you through this. Your textbook hasn't talked about degrees at all. It hasn't mentioned it once in the entire section, but I figured I might as well throw this up here. I don't know if that's helpful or not to talk about degrees. But we've been measuring the distances around the unit circle, and those have been the inputs. So this second line should be familiar. And then, of course, if you take as your input x, if this is equal to x, then the sine of this would be 0. Like sine of negative pi is 0. Sine of 0 is 0. Sine of pi over 2 is 1. And the cosine is down here also. So if the input is 0, then the output is 1 for cosine. But we've got these other outputs that we're learning now. We just learned about tangent, cosecant, and secant, and cotangent. This is how they're defined in terms of u and v, 1 and v, 1 over v, 1 over u, v over u. But we can say that these are the actual outputs right here. So we calculated these by hand, some of these. You can see, for example, the reciprocal of negative 1 for sine is going to be negative 1 here for its cosecant reciprocal. The reciprocal of 0 is going to be undefined when we look at the secant function down here. The reciprocal of 0 is going to be undefined when we look at the cosecant function. So, and let's even hone in a little bit. We've got on the bottom line, we've got cotangent here, and the cotangent is the reciprocal of tangent. So to state it with as much clarity as I can, if the input is 2 pi for the tangent function, then you get an output of 0. But its reciprocal is cotangent. I want you to tell me what its reciprocal would be right here as you fill in this chart. All of these are, the bottom 3 rows are reciprocals, and the tangent is the sine over cosine. You can get them from these two values here. What does the graph look like? So here's what a reciprocal would look like. So the secant x, here's the orange, in orange you see secant x, and the original dotted line is cosine of x. What you notice is the reciprocal of 1 is 1. So when the cosine has an output of 1, then its reciprocal is also going to have the same output, 1, because they're reciprocals of each other. And as you go down here, say 0.5, at a height of 0.5, then the reciprocal of that would be 2. You get down to 1/3, and the reciprocal of that would be 3. And then you can actually go down very close to 0 and get up, and its reciprocal would be get as high as you want. This kind of parabola shape arc is going, it's not a true parabola, but it looks a little bit like a parabola because it goes up as high as you want it to go, because this reciprocal cosine function goes down here as low as you'd like it to go, as close to 0. So at 1 over 1,000, like 1,000th of a unit up, very close to the x-axis, the reciprocal of that would be 1,000, very high up on the y-axis here for the reciprocal. And in fact, when you get down to 0 at this gray dot, when the input is pi over 2, and the output for the cosine function is exactly equal to 0, then boom, you've got an asymptote, because you can't take the reciprocal of 0. vertical asymptote right here. And then things go negative, and you repeat the same thing all over again. It's very symmetric in that way. The same exact, for all the same reasons that we created a U shape here, you also create a U shape right here. I can't officially call it a parabola, but it looks a little bit like a parabola. The reciprocal of -1 is also -1, so they touch right here. And so one easy way to sketch a secant graph is to first sketch a cosine graph. Here's the trick. If you need to ever draw a secant graph, then first draw its reciprocal, the cosine graph. So cosine, boom, 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 and then everywhere the cosine hits its maximum, the reciprocal, the secant function, will hit its minimum right here. And you just put some u's on top. These are like kissing u's. Oh, kissing u's. They kiss right here at 1 and -1. And when it's a negative, do a Google image search for kissing u's, and like instead of U, press a EWES. I'll bet you get like 2 lambs kissing each other. These are u's that are kissing each other right here. And then we've got the same vertical asymptote going on wherever the function is, whether the original cosine function is equal to 0. We could play the same exact game with secant. So if you ever need to draw a cosecant graph, first sketch out its reciprocal. That would be the sine of x. So you know sine of x is equal to 0 here. We have the values right here in yellow. So we can see that the output for the sine function is 0, but the output for its reciprocal cosecant function was undefined. That's visualized right here in the graph. So we've got this dotted line, this vertical asymptote right here, and the u's kiss right here at a height of 1 and a height of -1. Tangent. Tangent's going to be pretty tricky to graph itself. We've got these really crazy squiggles going on, separated by these dotted lines. Now, anytime the cosine, remember that tan of x is the sine of x over cosine of x. So, anytime the cosine of x function is equal to 0, the tangent is also going to have these dotted lines right here, these vertical asymptotes. The function starts out incredibly negative and then goes up to 0, because that's where sine of x is equal to 0 and cosine of x is equal to 1. So at this value right here, we have 0 over 1. And then it goes up to incredibly high values. And you can see that when you, if you were finding the slope, if the tangent is related to the slope, so then as this point goes up here, it starts, the line connecting the origin to the dot starts out at a very incredibly flat 0 slope, then gets to a slope of 1, and then gets higher and higher and higher and higher, and eventually the slope is undefined right here. The slope is undefined at pi over 2, when the distance around the circle is pi over 2. And then it starts out it's undefined and incredibly steep negative-wise, and then back down to -1, and then back down to 0. Back up to 0. So it's increasing from negative infinity up to 0, up to positive infinity here, which is reflected on this graph. Boom. The reciprocal of that would be cosine over sine, and it looks like this. So anywhere there's a sine graph that has a value of 0, if sine has a value of 0, then the cotangent is going to be dotted right here. Notice we've got asymptotes at -pi and pi and 0. 0, pi, 2 pi, 3 pi, 4 pi, -pi, -2 pi, and then we've got halfway in between the asymptotes, the function is equal to 0. Halfway in between, it's equal to 0. Halfway in between, it's equal to 0. Take a moment to make sure you've copied all of these down. And while you copy all these down, I'll just say that when I was in 8th grade, I went to the Gateway Arch in St. Louis. That's a national park, Gateway Arch National Park. You see the giant arch in St. Louis. If you've ever been there, let me know. If you went up in the elevator, I'm jealous because it was broken when I was there, and we were like scheduled to go, but it couldn't because it was broken. So it's kind of like a dark chapter in my life. All right, so let's take a look at this. We've got to ask these questions of ourselves. These are like function questions. We got to know, do things have, what are the domains? Are they even and odd, neither, periodic, all this stuff. The same questions we've always asked about functions, we need to start asking about these new functions that we're learning about. The tangent function, does it have any vertical asymptotes? Well, the sine and cosine don't, but the tangent does. It has vertical asymptotes at first of all pi over 2, and then 3 pi over 2, and 5 pi over 2, and 7 pi over 2. And one easy way to write that is pi over 2 plus n pi, where n is any integer. So we've got pi over 2, and then plus 1 pi, plus 2 pi, plus 3 pi. When you combine those together, that's what you get. The domain for sine and cosine, it's all real numbers, but for tangent, it gets a little tricky because it's all real numbers except anywhere it has a vertical asymptote. So you can see this pi over 2 plus n pi. That's like x such that x is not equal to pi over 2 plus n pi. If you're going to write that out in interval notation, then you could start out at 0 and go as negative as pi over 2, negative pi over 2, and then pi over 2. But then you got a vertical asymptote that you have to make sure you don't touch. And then from negative pi over 2 to negative 3 pi over 2. You can see that in the graph if you flip back in your notes. Secant is going to be the same, because remember the tangent can be defined as sine over cosine. So both secant and tangent have a cosine in the denominator of their fractions. So whenever cosine is equal to 0, tangent will have a vertical asymptote, and so will secant. They have the same vertical asymptotes in the same locations. And so therefore they'll also have the same domains. All right, so I just found a mistake here. If you copied it down earlier, I had to change this. The secant function, let's talk about odd, even, or neither. So the sine function is odd. You can rotate, it's rotationally symmetric about its origin, the origin point. Cosine is even, it has a reflection about the y-axis. Tangent is odd. You can, just like the sine function, you can rotate the tangent function about the origin and get an exact copy. The secant function is very much like the cosine function because the reciprocals, like secant and cosine, are reciprocals. So cosine is even, so secant is even. It's you can reflect it about the y-axis. Cosecant, let's talk about cosecant function. It has vertical asymptotes at 0 pi, 1 pi, 2 pi, 3 pi, 4 pi. That's where the vertical asymptotes are. And so you can write the domain as x such that x is not equal to all of the vertical asymptotes. X is not equal to n pi, where n is any integer. If you wanted to write that in terms of interval notation, you can't include 0 because there's an asymptote there. So you go from 0 to pi, and from 0 to negative pi, but not including 0 and not including pi. And then from pi to 2 pi, and from 2 pi to 3 pi, and onward. The cotangent is going to be the same as cosecant because they both have sine of x in the denominator as how they're defined. So wherever sine of x is equal to 0, then both cosecant and cotangent are going to have vertical asymptotes. Oh, you can see that on their graph. Both cosecant and cotangent are going to be odd functions. They're both going to be rotationally symmetric about the origin. All of these are periodic because they just repeat with the same period. They're based on the unit circle, and the unit circle itself is periodic. But the one little trick, one little thing to note here is that the period itself, although sine and cosine have a period of 2 pi, tangent has a period of pi. The period is half as long. It's only pi. The graph of itself repeats every pi units. The same thing with cotangent because they're reciprocals of each other. They'll have the same period. So I know we talked about amplitude with sine and cosine. It doesn't really make a whole lot of sense to talk about the amplitude of tangent, secant, cosecant, or cotangent. So let's talk about the range instead. The range of tangent is going to be all real numbers because, and in fact it's going to be the same for cotangent because those squiggles go all the way up as high as positive infinity and all the way down as negative infinity. And you might think upon first thought that secant and cosecant are the same because they have those u's that go all the way up to positive infinity and down to negative infinity. But in fact, there's a little break in the middle where the x-axis is. The secant and cosecant functions, the u's don't extend all the way to the x-axis. They only go as, like the positive one only goes as low as 1. And the negative u only gets up as high as -1. So these are the collection of all the y values. y values in the secant function, like of 0 or 0.5 or 0.999, are not represented in the secant function. The same for cosecant. I'll show you what all that looks like on the graph, or maybe you can see what it looks like on the graph. But of course, I'm throwing a lot of information at you, so if you have questions, I want you to write them down and bring them. Now is a good time to write your questions down and bring them to class. Go ahead and copy the assignment list and start the first problem from assignment 62, and I'll see you in class.